This is a revision video which will give you a chance to refresh your memory in terms of what you know about the rates of chemical reactions and how to study them. So, here are the first set of learning outcomes for this video. So you'll need to make certain that you know how to work out a rate of reaction from experimental data. You'll need to know some of the ways in which familiar chemical methods can be used to follow a reaction and hence work out the rate of a reaction. And you'll need to have some idea then about how you would design the key features of experiments that would enable you to measure the rate of a reaction, and how then you would use the information from those experiments to actually calculate the rate of a chemical reaction. Okay, so what do we mean by the rate of a chemical reaction? Well, usually, and certainly in examination questions, you can be fairly certain that the rate of reaction is defined as the change in the concentration of a reactant divided by the change in time to produce that concentration change. It is possible, certainly in experimental work, to measure rates of reaction using other definitions, but that's the most usual one that you'll come across in exam situations. The units of rate of reaction therefore will be moles per decimeter cubed per second. Just check that you are happy that you can understand where that unit comes from in terms of the equation that we've just written up here. Okay, so given that equation then to work out the rate of reaction, how would we do so? Well, practically we would be able to follow a reaction over a period of time, and if we measure one property of that reaction mixture over that time period, we will be able then to work out the rate of a chemical reaction. So, having understood in general terms how we're going to calculate rates of reaction from data, what methods are available for following a chemical reaction? There are certain ones that are required by the exam. Let's look at a fairly familiar reaction that you've studied before. So it's a reaction between manganate ions in the presence of acid, and they'll oxidize Fe2 plus ions to produce Fe3 plus ions. How might you attempt to follow the rate of that chemical reaction? Just pause the video for a moment and see if you've got any thoughts. Well, of course, the feature that's most obvious about this reaction is that the manganate ion is extremely strongly coloured, and therefore we can monitor its concentration by using the familiar technique of colorimetry. And you should be able to describe how to carry out colorimetry, including details such as the calibration of a colorimeter, so you can convert absorbance readings into concentration terms from work you've done in earlier units. Okay, let's look at another possible reaction we may want to follow. So this, perhaps less familiar, it's a reaction between iodine, and this is the molecule propanone, and iodine will actually react with propanone to produce this iodinated compound plus hydrogen iodide. Now, how might we follow the rate of that reaction? Well, give yourself a chance to think about it and pause the video, and when you're ready we can restart. Okay, well, the substance to focus on here is iodine, and probably the thing you may well have imagined is that we can use the colour of iodine to follow that reaction using a colorimeter, and of course that's absolutely right. But it's also possible to find the concentration of iodine by another technique, and many of you will be familiar with this from your investigation. We can use titration to find the concentration of iodine. So iodine is a titratable substance along with things like acids and alkalis, and therefore we can use titration. Now, need to be a little bit careful here, because of course what you'll have will be a large reaction vessel in which iodine and propanone are reacting. You'll need to extract small samples at certain time intervals and carry out a titration. Just pause the video while you think about what you would titrate iodine against in such a titration. And you should be familiar with the idea that we can use something called sodium thiosulfate. You would probably find that the equation for that reaction would be provided for you if you then needed to do some calculations to work out the concentration of iodine. And finally, a slightly simpler reaction. So here's a reaction where hydrogen peroxide decomposes to produce water and oxygen. So again, pause the video and think about how you might follow the rate of that reaction. This will be extremely familiar to some of you because, of course, a gas is evolved, and so the easiest way of following that would be to use a gas syringe to measure the volume of gas produced. So here's a summary of the techniques that you could use to follow these reactions and hence work out the rate of the reaction. In each case, though, there are other possibilities that you could use as well. So you might like now to rack your brains and try to work out possible alternative methods that would work. And here we are. The point about something that produces a gas like the hydrogen peroxide reaction is, as well as collecting the gas, you can simply place the reaction vessel on a balance and measure any mass change that you might get. It's sometimes disappointingly small, the mass change, but it's certainly a valid way of collecting data. The coloured substance, the manganate here, the colorimetry, will notice that in the reaction mixture H+ ions are used up, so it's possible that we could monitor the reaction by measuring its pH, or possibly taking small samples and measuring the H+ concentration by titrating it against alkali. It's even possible to extract the manganate and carry out a titration in which you measure the manganate concentration. And finally, the iodine and propanone reaction. Well, we talked about using titration of the iodine using sodium thiosulfate, and we mentioned, I think at that time, that you could also use colorimetry. One possible other method is that HI, the final product produced here, is acidic, and therefore you could imagine titrating that. So you may need to be fairly creative about the ways that you study these reactions. Okay, so you've described in very general terms how you would follow a reaction. How then will you use the data that you get from such an experiment to actually calculate or measure the rate? Well, the key to it is plotting what I always call a progress graph. In other words, measuring the property over a period of time and plotting that property against time. What will a progress graph look like? Well, here's an example. So this would be the kind of data you might get from, say, the manganate reaction, whereas the manganate colour fades over time, the absorbance reading in the colorimeter would also gradually fall, and we'd end up with a graph looking something like this. Pause the video while you think about why the graph might have this particular shape. Well, of course, the point is that the slope of the line on the graph here gives you some indication about how fast the reaction is occurring. It's very fast at the beginning, much slower at the end. Why might that be? Well, of course, reactants are being used up, and so the concentration of reactants is falling, and that makes the rate of reaction a lot slower towards the end of the reaction. And that's the reason why we're particularly interested in the rate of reaction at the start, what we call the initial rate. It's the only time in the whole experiment when you actually know the concentration values of the reactants, and therefore that's going to be the most significant rate to measure. So how do we measure the rate if we've got a graph like this? Well, we can plot something called a tangent. With a tangent, you basically hold your ruler against the curve and attempt to, as far as possible, mimic the slope of the curve at exactly the starting point of the reaction t equals 0. And I've done it rather roughly on here, but you can see that we get a straight line, and we can calculate the gradient of that straight line. Okay, and the gradient, of course, is given by the change in the vertical axis, in this case absorbance, divided by the change in the horizontal axis, in this case time. Okay, another progress curve here. This is a progress curve you might get from the hydrogen peroxide experiment, where you are collecting oxygen gas at various time intervals. You'll notice here that the graph actually slopes upward because, of course, we're measuring the amount of product produced. But you can still use that idea of the tangent at the beginning of the reaction to work out the rate of reaction right at the start, where we know things like the concentration of the hydrogen peroxide. Notice, by the way, that the gradient that you obtain here has units of centimetres cubed per second. Probably in exam questions you'll find that usually they actually make the vertical axis a concentration axis, and therefore your gradient should give you a rate in moles per dm cubed per second. But of course experimental data usually isn't quite that easy. Now one thing you'll notice about this graph is that for the first sort of 3 or 4 data points, the graph is almost a straight line. There's a distinctly linear section here. That's extremely helpful if you are doing an experiment, because it does mean that the rate of reaction that we get is much more reliable than if we're having to guess at the slope of a tangent in a graph that's rapidly changing slope. Now that's achieved by deliberately using an excess of, say, hydrogen peroxide, so that it doesn't change very much during the first few seconds of the reaction. And so using an excess of a reagent is a helpful way often of getting a linear graph, and so people very often tweak the reaction conditions to ensure that that is the case. So what we've found is that it's perfectly possible to be able to find the rate of a chemical reaction from experimental data. Now that in itself is not a particularly valuable exercise. What we want to do really is to continue with that investigation and find out how the rate of reaction then depends on certain variables. And typically the one we might want to investigate would be concentration. How would we do that? Well, it's quite simple. We simply repeat this experiment, but we vary the concentration of one or more of the reagents. Of course, you'll only vary one concentration at a time, but if we do so, we'll end up with graphs looking something like this. So you can see here a variety of progress curves for a range of hydrogen peroxide concentrations. That's not the end of the story, because of course for each of those progress curves we need to calculate a gradient from taking the tangent, and that information really ought to be summarized in some kind of table of processed data. So you'll end up with some data that will look something like this. At this stage in the video I'm not going to do very much more with this, but certainly you'll recognize this kind of table of processed data if you've done an investigation using rates and looking at the way in which rates depend on concentration. We'll focus more on how to analyze this kind of data in the next video. So in this first video you've reminded yourself of the meaning of rate of reaction, how it's calculated from experimental data, and also looked at experimental techniques that can be used to produce that kind of data. So do feel free to watch the video again, or if you can find the second video on the playlist, then you'll be able to follow this up by looking at how the information that we get from these experiments can be used to derive things like rate equations.